everyone. Today we are going to talk about multivariate SPC. We will discuss about the motivation of multivariate control chart after background about multivariate statistics and statistical distance. We will learn about the Hotelling's t-square control chart. In practice, there can be more than one quality characteristics to be monitored. And more importantly, they can be dependent on each other. Someone may ask, can we monitor a multivariate process using multiple univariate control chart? Okay, here is an example. Suppose that a process has two related quality characteristics, x1 and x2, and they have independent normal distribution. Then we apply the usual X bar chart to each characteristic. Then it is in control only if X bar 1 and X bar 2 fall within the shaded region in the figure. However, if you look closely at the shaded region, there is data point in the upper left corner that is quite far from the other data point. Although it looks like anomalous data, the multiple univariate monitoring approach fails to capture it. Two major limitations have been reported in the literature for the use of multiple univariate monitoring chart for multivariate process. First one is that a proper design is quite complicated. Each univariate SPC control chart has its own procedure parameters. Thus, this would have many parameters to determine before it can be used. The other one is that using multiple univariate monitoring chart is theoretically less powerful. For example, to test the possible difference between two p-dimensional population means, it would be more powerful to treat the two population means as two vectors and compare them by multivariate testing procedure than to utilizing p-univariate testing procedure jointly. There are many types of multivariate monitoring chart. In this lecture, let me introduce the multivariate version of a Schwartz control chart. Similar to Schwartz control chart, we assume that multiple quality characteristics follow multivariate normal distribution. Formally, bold X indicates a vector which consists of values of p variables. Bold X follows a multivariate normal distribution with the mean bold mu and sigma metrics. Here, P indicates the data dimension or number of quality characteristics, and bold mu is the population mean vector. Sigma is the population covariance matrix. Its PDF is well known as shown in the slide. The univariate version of normal distribution PDF is a special case of it. Okay, this PDF, f of x, represents the likelihood of obtaining x as an observation from normal distribution mu sigma. That is, if the likelihood is very low, then we regard the x as anomalous data or out of control. To explain this concept more clearly, let me introduce the statistical distance. The statistical distance from x1 to x2 is defined as a square root of mean difference times inverse matrix of covariance matrix times the mean difference. The term looks familiar, right? Yes, this term from the PDF of multivariate normal. This statistical distance measures the likelihood of obtaining x as an observation from a population distribution. This distance can be compared with the well-known Euclidean distance. Look at this figure. Consider a multivariate normal distribution with mu 5, 5 and the covariance matrix 1, 0.45, 0.45, 0.25. We have two data points, 4, 7 and 7, 6. Their Euclidean distance to mu equal to be 2.22361, but the statistical distance are different. Which one is shorter? The statistical distance from 4, 7 to 5, 5 is 11.29, and from 7, 6 to 5, 5 is 2.05. So 7, 6 to 5, 5 is shorter because the likelihood of obtaining 7, 6 as an observation from the distribution is larger. In other words, 4, 7 has a higher probability to be abnormous. Based on this concept of the statistical distance, we can construct the charting statistic of a multivariate short control chart. Let us consider the phase 1 problem. X1 to Xm is a phase 1 data set obtained from p-dimensional production process. The IC distribution is known as a multivariate normal distribution with mu 0 and sigma 0. We are interested in detecting any mean shift in the process. Note that mu 0 and sigma 0 are both known. At the ith time point, it is natural to consider the charting statistic t-square based on the concept of statistical distance. Because this statistic is known to follow chi-square distribution, it gives a signal of a mean shift if t-square is greater than 1 minus alpha quantile of a chi-square distribution. One of the popular detection method for multivariate cases is the Hoteling's t-square control chart. Depending on distribution parameter availability and the sample size, there are many cases of the Hoteling's t-square control chart. We just showed the result of case 1 in the previous slide. We're going to skip the details of other cases in this lecture. Instead, let me summarize their test statistic and upper control limit. Note that the test statistic is related to the concept of statistical distance. We only regard the data having a large distance from the center as out of control. That is why upper control limit is matter. Here is an example of a multivariate SPC. The tensile strength and diameter of textile fiber are two important quality characteristics that are to be jointly controlled. The quality engineer has decided to use sample size 10 fiber specimens in each sample. It has taken 20 preliminary samples. And on the basis of these data, he estimates distribution parameters. Suppose that we need to set up the phase 1 t-square control chart. Because this is a phase 1 problem, mu 0 and sigma 0 are unknown and n equals to 10. So we can apply the case 3b, Hoteling's t-square control chart. Because mu 0 and sigma 0 are unknown, we use the estimate of them. So here is the computation of t1 square based on the test statistic of case 3b from the table in the previous slide. In this way, we can compute t1 square to t20 square and upper control limit as shown in this figure. Similar to the Schwartz control chart, the Houghton-List t-square control chart also has difficulties in detecting small mean shift, particularly in directions where the statistical distance between the two means is small. One way to improve it is to use a large sample. Let's discuss the sample size effect in the Houghton-List t-square control chart. Here is an example, illustrative example. Suppose we try to detect a mean shift to 3.6 from 2.5 when n equal to 1 and n equal to 10. As the figure shows, both probability ellipses have the same shape. The n equal to 10 ellipse has a little overlap with the acceptance region as compared to the previous n equal to 1 case, where the overlapping is large, here the dashed line. So with a large sample, the overlap region decreases and the mean shift can be easily detected. Now let's discuss about detecting covariance change. The following example illustrates the changes in the covariance matrix can cause out of control outcomes in a t-square chart. Suppose that we want to detect covariance matrix change from sigma 0 to sigma 1. Since neither the mean or covariance, mean or the variance of x1 or x2 has changed, it would be difficult to detect the change had we used to multiple univariate control chart. But t-square chart detect this change. Okay, this figure shows the sample data from two different multivariate normal distributions having the same mu0, but the different covariance matrix. Also, it shows the corresponding 1 minus alpha quantile of a chi-square distribution. Definitely, t-square chart is able to distinguish the covariance changes. So if you look at the X bar chart for X1 and X2 and t-square chart, we can see that the t-square chart successfully gives a signal for the change in the covariance matrix. However, because the t-square chart is sensitive to all kinds of changes, it also makes the interpretation of out of control conditions to be difficult. So unlike the univariate cases, t-square does not have a separate control chart on mean and variance or on covariance. Therefore, it is difficult to identify the root cause. So we need to use together sometimes with the univariate chart or other tools to help pinpoint the root causes behind an out of control condition. Okay, let me summarize today's lecture. Today we talked about multivariate SPC for multivariate process, where there are more than one quality characteristics. Among multivariate control chart, we learned the Houghton-List t-square chart, whose test statistic is motivated by the statistical distance. However, similar to the Schwartz control chart, it has a limitation in detecting small mean shift. To increase the detecting power, we can consider to increase the sample size. Unlike the Schwartz control chart, the t-square chart is able to detect covariance change as well. Thank you.